So, we have not, I think the only thing that we have not talked about for scales, we've talked about the magnitude scale, we've talked about the luminosity scale, we haven't mentioned radius. There is also a pattern for radii. Now, also, I'm going to show you a graphic that probably doesn't show it well enough for you to see on this graph, but once you get the PowerPoint, you can that goes along with this, you can zoom in and see it better. This particular graphic for instance, it has the lifespans on here. We have the sun at 10 billion years all the way up to a lifespan up here for some of these stars of only 10 million. But there's also a series of lines that go horizontally across this graphic, starting at the bottom and going at the top, and they are from least to most largest radius of the individual stars. Obviously, looking along the main sequence, these little red dwarfs have a much smaller radius than the sun, which has a much smaller radius than a more massive star. So as you go further and further up the main sequence, the radius gets larger and larger. If you move up to the giant branch, the radius gets even larger because these are very expanded stars in the later stages of their evolution. You get up to the supergiant branch, they're even larger in radius. However, down here in the white dwarf branch, these stars have a very, very small radius. So the smallest radii are on the white dwarf branch. The largest radii are on the supergiant branch. So it comes down to the only sort of mathematical parts of this are two things, the distance modulus and the inverse square law. The distance modulus is simply a relationship between three variables, absolute magnitude, apparent magnitude, and distance. If you know any two of those variables, you can find the other one. That's why this one is one of the methods of determining how far away things are in the universe. By if you know the absolute and apparent magnitude, you can determine the distance. With the absolute magnitude equals the apparent magnitude minus 5 log 10 distance over 10. That's essentially the same thing as simply taking all those stars out there and putting them at the same distance from the Earth to determine how bright they actually are. Takes that into consideration in this relationship. So if you study the spectra of a star, you know its luminosity. There's a relationship between luminosity and absolute magnitude, so you can determine the absolute magnitude. You know the apparent magnitude just by looking at it, so that's all you need to do to determine the distance. The inverse square law simply says if you move a source twice as far away, then it's going to cover 4 times the area, and so it's only 1/4 of the intensity of the brightness of the star. If you move it 3 times out, it's going to cover 9 times the area, so it's 1/9 of the intensity the brightness is, so that's L luminosity equals 1 over R squared. Here is another HR diagram that's a little bit different. It has the luminosity and the absolute magnitude on the same scale. This one has subclasses listed, so it has different spacing between the classes. It also includes planetary nebula central stars. Don't let that mislead you. Those are white dwarfs. Planetary nebulas cannot be plotted on an HR diagram because there's not one specific unique temperature. It's too expanded. Here's another HR diagram, and the only reason I include this one is because right up there, it actually has Zeta Orphiuchi on this HR diagram. So that's where Zeta Orphiuchi is, that really massive hot O stellar classification O 9.5 star is located on the diagram. Blackbody radiation, Planck's law and Wien's law. Blackbody radiation is a mental model, a theoretical construct that is an object that absorbs every single bit of radiation that falls on it and then radiates every bit of that radiation back away. So it neither gains nor loses any energy. It takes everything that comes in and gives it all back away again. And a stellar atmosphere is a pretty good approximation of a black body because it has all that radiation coming in from the fusion process taking place in the core. So all of the radiation coming from the core, all wavelengths are absorbed by the atmosphere, and then it radiates it all away into space-time. So that's why we see those absorption lines coming out of the surface of the atmosphere of stars, because they've absorbed everything that's reached them, and then they re-radiate it all away. So that's what blackbody radiation is. And Planck's law simply says that a star will emit its radiation at every single wavelength more than a cooler star. Look at this graphic, for example. We have the yellow star in the middle. It says it has a temperature of 6,000 K. So if you look at the line of produced down here, it comes up and it reaches a peak and then it slopes back down. Nowhere does that line dip below the cooler star, the 3,000 K star below it. At no point does the radiation coming from this big hot blue star, at no point does any of that radiation, whether it's infrared, ultraviolet, optical, X-ray, whatever, it doesn't matter, not one place along that entire electromagnetic spectrum is that wavelength going to produce less wavelengths than a cooler star. Always more than. So you can see the hot star, the blue star never goes below the yellow star never goes below the red star. And that's Planck's law. Wien's law tells you that every single star has a wavelength at which it produces its maximum radiation, its maximum wavelength, which is, of course, dependent upon its temperature. So you have, for instance, the blue star has a temperature of 12,000, and the relationship to determine that the maximum wavelength is the peak wavelength that every star produces is equal to 2.9 times 10 to the 7 divided by T. Okay? T. So that's the temperature. So if you know the temperature, you know exactly what wavelength is the maximum output wavelength for that individual star. The blue star here, it says it has a maximum output of 250 nanometers. Well, that falls in the ultraviolet range. The next star, the yellow star, has a maximum output of 500 nanometers. Optical falls between approximately 400 and 700 nanometers. So that the maximum out peak for that particular star is in the optical part of the spectrum. And then the cooler star, its peak wavelength is 1,000 nanometers. That puts it in the infrared part of the spectrum. So we would not see visual optically its maximum wavelength. So that's the blackbody radiation, Planck's law, and Wien's law, which you should have an understanding of. For resources, the first resource you should go to, besides the webinar, are what they have located on the National Science Olympiad website, soinc.org. There is an astronomy manual that was written in 2010. I think I updated. Maybe it's time to update some more. 2010 manual for astronomy that works equally as well for the B division as it does for the C division. They have a source Biology Earth CD, and it gives a lot of learning tools on how to prepare for events with some with some past events on there also, how to prepare for events. They also have, on the B division, they have the test packet for the 2016 competition. And that test packet includes, I think they're $18. The test packet includes the Reach for the Stars event and G, the entire event with the answer key. And guess what? It's almost identical to this year's event. And most of those deep sky objects that were on there and most of those constellations were on the 2016 event. So that will give you a really, really good practice for learning the competition this year. So you should stick to the science websites. Stick to, Chandra, Hubble, Spitzer. APOD is great. It's supported by NASA. So you should use those. Also, one of the resources is the National Audubon Society's Night Sky for this event.